So now let's look at the transformation. Now, what are the different transformations that are available? They have just listed it up. Now so you have downloaded the data. Uh, Now the transformation that we preferably use is 2 tensor, which is mandatory. Now there are some more transformations. No, it's not elaborated here. There are some more transformations that we shall be using, like random crop, resize. All those things we will look at in so whenever we get the time of it. Whenever we are looking at that code, then we will be telling you how your input features has been transformed. Okay. Now this is the first step. The data is ready. Okay. Now you have curated the data. So now comes the next thing, which is your build the network. Okay. Now we should be building the network. So now whenever the next step, which is build the network. Now first you should know what are the choices of network. Now I'm assuming that we are in this task. Now we are dealing with image classification. Okay. But almost similar principles holds for other modalities as well. Now, whenever you have image classification, now the very crudest form that we can do is we use an MLP or we use CNNs. Okay. Or nowadays you can use even the vision transformers, VTs. Now this is VTs are for future. Okay. Now this is for so we will not be looking into VTs as of now, vision transformers. Preferably, we will be looking into multilayer perceptrons and convolutional neural networks. Okay. So now, whenever I say convolutional MLP, now let's take the first case of MLP. Okay. This MLP. Now, there are some choices that needs to be made. Now, the choices are, the first thing is how many layers. Okay. And how many nodes in each layer. That also needs to be decided. And what is the activation function that needs to be used. Okay. Now these choices needs to be dealt with. Okay. So now let's take these choices into hand and then create an MLP. Let's go ahead with that. Yeah. Now let's build a neural network. The first thing is OS. Now why do you need OS? Now if you are retrieving anything from the system, the torch for the PyTorch. Now torch import NN. Now this NN stands for neural network. Now data loader is needed to get your data, and then dataset and transforms are needed to transform your data. Now these are the libraries that we have already seen. Okay. Yeah. Okay. This is something that we haven't looked at. Now, how do you get your device? Let it run. I'll rerun it again. I should have told you how to get the device first. It will take some time to initialize all these libraries. These are very big libraries. Need some time to initialize and establish the connection. Yeah, okay. So now, if you click it here, and then you can see here change runtime. Now, when you look at this, these are the available devices for free. Okay, a CPU is there, a T4 GPU is there, and a V2 8 TPU is there. I'll use this T4 GPU. It will say that it will terminate your current session. Okay, let it terminate, no problem. I've saved it. So now everything that has stored in the previous thing, all of them will be removed. So I need to rerun this so that all these libraries are reloaded again. or you can change this. You go to this runtime. You can change this, change runtime, and then change it to GPU, CPU, back and forth. You can work it out. Yeah. Now, torch.accelerator, current accelerator, if it is there, use it, else you use a CPU. Yes, now we are using the CUDA device. Now, CUDA is the name that is given for this all these GPU devices. Okay, yeah, fine. I'm using the CUDA device now. So now let's create a neural network. That is what so we are intending to do now. Okay, let's do it. Now we have to create a class of this. Okay, class neural network, whatever name that you want to give, and that has to be the child of the parent called as nn.module. Now that is the name of the parent. Okay, fine. So now in the init method, in the constructor, you have the self. If you want any other arguments, you can pass it on. And then you call super. So that means that you are calling the parent's init method. Okay. Now init method is used to initialize all the parameters that are there. Now, what is the first thing that you are supposed to do? Okay. Now, since you are doing an MLP and your input is if we are taking fashion MNIST, which is a 28 cross 28 matrix, it's a single channel image, and then the input for your MLP will be a vector. Now, you need to convert this into a vector. You need to flatten it up, because of which the outcome now will be a vector, which is cross 1. How do I get this 784? It is 28 cross 28. Now, how do you do it? You take the first row, put it here, take the next row, put it here, the next row, put it here, now so on and so forth. You put it, and then you get a 784 cross 1 block. And this process is what is called as flattening. So now you have a vector, which is of size 784. Okay. So now your input dimensions are fixed. Okay. Now which is 784, and your output dimensions are fixed, which has to be 10, because you have 10 classes. So the final, it should have 10 thing. You get the logics out of it. Now I presume that you know the theory, and then you pass it through a softmax method. You pass this through softmax. You pass this through softmax now and get a probability vector out of it. Okay, of size 10 cross 1. We are taking the case of FMNIS, which is a 10 class problem. So we'll have 10 cross 1. So now the thing is, what is there in between? Now you need to look into it now. Now this is what you should decide. How many layers should be there? Now your input nodes are fixed, 784. Now you have this 784 things. Your input nodes are fixed. Now how many hidden nodes and how many nodes at each thing now has to be fixed. Okay. So now let's look at the code that is been given. Okay. Now first you go ahead and do self.flatten, now wherein which the image that you have, you're flattening that specific image, and then what you're doing is you're creating, the next thing that you're doing is you're creating a pipeline. Now, the idea of pipeline is pretty much simple. Okay. Now you have multiple processes. Okay, you pass your input. The output of the first will be the output of the next, like this, like this, like this. Now, what you do, rather than creating each one of them separately, you create it as a single entity. Okay, you create this whole thing as a single entity, and then you can make use of it. Now, this is the idea of pipelining. Okay. That is what is being used here. Self dot linear ReLU stack. I'm using the activation function ReLU. So now ReLU stack nn dot sequential. Now that means that, now, as I told you, it's a pipeline. The output of one thing is input for the next stage. I'm using nn dot linear. So this is the first thing. Now you create one layer. Now he's saying that 28 cross 28 comma 512. Now what does that mean? You have this 28 cross 28 now, which is your input. Now then the next thing that you have is a 512. Okay. Now this is one thing. This is one. Okay. Now this is normally, this will have a weight vector now, which is a matrix now, which is of size. This belongs to R 784 cross 512, and then you have the bias, which is in R. First one is in R5. Okay. Now this is the first layer that you have specified, and then the output of which, after this transformation, now 784 into 512, now using an MLP, you multiply it. Now how do you multiply that? Okay, so now all the MLP, you can think of it like, if you have your input X, okay, now you have this W, this W transpose X now is one forward propagation that you have. Okay, so now if you take any X, now in this case my X will be a 784 cross 1. Okay, and what will be my W transpose? My W transpose will be 512 cross 784. Okay, I can multiply these two things, so the outcome will be a 512 cross 1. This will be the outcome. Now to this you will be adding this B1, which is a 512 length vector. Okay, now the output will be a 512 cross 1 vector. Okay, now this is one step. Okay, so now that means that every propagation in the neural network, you can think of it as a matrix and vector multiplication, or matrix multiplication in case of convolutions. Okay, so and then the output which is there, the output that you have got, the 512 length vector, now that you pass it through a ReLU activation. Now we know what is ReLU activation. Just to give you a recap, now if your input is Z, okay, now it will be 0 if the Z is less than or equal to 0, Z if Z is greater than 0. Okay, now this is the rectified linear unit, now ReLU activation that has been used. So now this 512 length vector will be passed through this ReLU. That means that each and everything, now you have first element, now it will check whether the first element is less than 0 or greater than 0. If it is less than 0, it will become 0. Like that, for each of the element, it will check individually. Okay. Now that you are applying this ReLU activation. Now after that, again you have one more 512 to 512. Now that means that you have fixed this 512. Now this is the input. Now from here, again you have a 512. Okay. Now that means that you have one more matrix now here, W2. Just please bear with me here. W2. Now this is of the matrix of size 512 cross 512. Okay, and then your biases too now will be, for each node there will be a bias. Okay, so now you have let's call this with some, you have a 512 cross 1 that you multiply with W2 transpose. Okay, now which is again 512 cross 512. Now you multiply this, you get a 512 cross 1. To that you add B2, which is a 512 length vector. Now it will be a 512 cross 1. Okay. The output of this is a 512 cross 1 now. Okay. Again, you use a ReLU activation here. And then the next layer is you have 512 to 10. That means that you have 512 here to 10. This is the next matrix that you are considering. Let's consider this as W3. Now this is our 512 cross 10. Here B3 is a vector size 10. And then what happens? You have this 512 cross 1 that you multiply with W3 transpose. What is this W3 transpose? It will be 10 cross 512. Now this outcome will be 10 cross 1. To that you will add B3, which is a 10 length vector. So the output will be a vector of size 10 cross 1. And then this is what is called as logits. That you pass through the softmax function, okay, to get posteriors, which we call it as P. This is softmax of whatever the vector that is there. I just bring it here since I haven't given any names to it. Now this will be your probabilities. This will be your posterior probability. Now this is, to be more specific, this is P of y given x. Okay. For a given x, what are the probabilities that we have has been obtained from this neural network. Okay. And please remember that for the last layer, you should not use any of these activations. Don't even put ReLU or activations or sigmoid or anything. Now you should leave it up like that. Okay. Now this is your whole structure. Now here, see, you can use different activation functions. You can use different number of nodes. Now, all those things are up to your choice. Okay. And then the forward method, now, which is your forward propagation. Now, first you flatten it. Now, that means that you have this 28 cross 28 matrix, which is converted into a, what do you call it, 784 dimensional vector. And then you pass it through this ReLU stack. Now, that means that first it will be transformed to 512, 512 to 512, and then 512 to 10. Now, you get the logits, and then you return this logits. Okay. Now, this is the class definition. And then here you are creating the instance of the class called as a model. Now the neural network, now you're creating an instance, and then you are pushing it into device. Now that means that till now it was on CPU. Now you are saying that now you deploy this on the GPU which you have. Run this. This is the network that we have. Okay. So now let's take a simple input, and then let's see how it works. I take an input, which is 1, 28 cross 28. Now this is my input. And then I'm placing it on the device. Okay. I'm directly placing it on the device. This is a random input. I don't know what it means. And then model X. Now this X, you're passing it through the model. Now that means that it will undergo this forward pass, which is nothing but the transformation. And then you get the logits. Now those logits, you pass it through the softmax function. Okay. Now that will get you the probability vector. And then you choose the highest of that probability vector, which will your class. You have 7 is your class. This is a random input. So now we don't need to worry about it. It doesn't have any, what do you call, significance here. Now once we take much more classic example, it will be clear. Okay. Now this is how you build a neural network. Okay. So now let's go back. Now, what are the things that are ready now? Okay. The things that are ready as of now is your data is ready. Data is, sorry, I could have data is ready. And then your network is ready. Okay. Now these two things are done. So now the next thing that is needed is how do you optimize this thing? How do you solve this? Okay. Now for that, you need an optimizer. So I will not be specifically going into this automatic differentiation, which is your how do you calculate the grads and thing. All those are internally taken care. Now I will not be delving deep into it because we'll not be needing those ideas. We can look into this. It's a pretty simple, straightforward thing. Now, how do you optimize the model parameters? Now, let's directly go into that. Let me close this off. How do you optimize these model parameters? How do you obtain these values? Okay. Now, yeah. Now, this is the prerequisite code. I presume that you are comfortable. These are necessary libraries. You are loading the data sets. Okay. And then you're creating an instance. The model. All those things are ready. Okay. Setting up the connection. It will take some time. Do so. Let's go back. Let's once it's done, let's look at it. Now, whenever we want to optimize it, so we will be using gradient descent. Okay. Now, what is the equation of the gradient descent? Now, W equals W minus some alpha times whatever is the loss with respect to the W. Now, all those ij I have just removed it. Now, this is the gradient descent. Now, if you're using a batch of it, this is stochastic batch gradient descent, SGD, as it famously called as. Now, you have this alpha, which is your learning rate. Okay. Now, we have many ways in which you can solve this. Now, one is what is the plain SGD, is one way. And we have this RMS prop. We can, this is one more solver. I'll not be going deep into this. I'm just giving you the names so that you can read through how is one different from another. And then we have this Adam. Okay. Now this is an adaptive method with momentum. That is why it is called as Adam. Similarly, these are some of the famous methods. Now, with using one of these, you can solve this problem. Yeah. So for that, we'll be needing learning rate, also called as step size, which is 10 to the power of minus 3. 1e minus 3 is 10 to the power of minus 3. And then you have a batch size of 64. Then you are running it for 5 epochs. Okay. Yeah, all your things are done now. Okay. Now, and then you need a loss. You're using the cross entropy loss. The CC loss, as it is famously called as. Now you need the optimizer. Okay. Now you are optimizing on these parameters, all the model dot parameters, all the parameters of the model. Now, if you want to only do it on certain set of parameters, even that can be done. I will look at how to do it in the coming sessions. Okay. Now torch.optim.sgd, you're using stochastic gradient descent on all the parameters. Now what is the learning rate? 10 to the power of minus 3, which we have declared just in the previous. And then let's look at the training loop. Now it's interesting. Okay. Now let's look at the overall training loop. Okay. This is a function. Now the function will be called only when the function call is made. So now let's go to the path first. Now you're creating an instance of your loss, cross entropy loss. Optimizer you're using SGD. Now epochs is 10. Now that means that you're running it for 10 epochs. Okay. Now for each epoch, you'll be doing this. What are you doing? First you print something. Okay, fine. Now then you are calling train loop. Now that means you are calling a method. You are calling a function. Sorry, it's not a method. It's a function. Train loop. Now to that you are passing the test loader, the train loader. You are passing the train loader, model, loss function, and optimizer. Now these are the parameters that you are passing. Now let's go there here. Okay. So now you are in the train loop. Now you have the data loader, model, loss function, and optimizer. First, you have calculated the length. Okay, let's try to understand this overall thing much more clearly. We are in the train loop. Okay. First, we have the first step that we have done as the size. Okay. This is number of examples. Okay, now we have obtained that. Now model dot train. So now every model that is there now will be in two phases. Now one is either in training phase or it will be the evaluation phase. In the training phase, now you need to actually go ahead and compute the gradients. In the evaluation phase, you don't need to look at the gradients. Okay, fine. So now you're saying that put the model into the training phase. And then you're saying that, okay, now enumerate on the data node. Now what happens when you say enumerate is, now enumerate uh, this D, I'm using this data loader, using this enumerate. Now what happens, what is this D? Now D1, D2, so on till Dk, right? Now how are they indexed? Now this is index 0, 1, so on till k minus 1. These are the indices. Now what are the values? Now it is saying that batch, comma, x and y. This is what it is saying. Now first the 0 which is there will be assigned to this batch. Now, because of enumerate, now the index will go here. And this D1 now will come to this tuple. Okay. When with x and y are there. Okay. Now you have got the batch index as well as x and y. Now this is what enumerate does. Now then you compute the forward pass. Then you perform the forward pass, get the predictions. Now once you have the predictions, you calculate the loss. Okay. You calculated the loss. Now if you remember, those are the steps that we looked at even in our earlier tutorials. Just for a recap, I'll just open that specific thing. To have your x and y, now first you calculate the prediction, then you calculate the loss. That is the second step that we need to be doing. We have calculated the loss. Then loss dot backward, now this will be computation of gradients. And then optimizer dot step is where you update the values. Okay. The four steps: the prediction, computation of loss, obtaining the gradients, and updating the weights. And then optimizer dot zero grad. Now what it does is, now there will be an accumulation of gradients that happens. Now after each gradient step, now what you should do is, now you should refresh the gradients and make it as 0. Okay, all the gradients has to be make it as 0. Now, otherwise it will be having issues. Okay. So now those are the steps that you are doing. Now when your batch is divisible, a multiple of 100, then you loss dot item. That means that you expect only the numerical value from this loss. Now why only numerical value? No, because this loss is not just number. No, it has something more to it. There is something called as computational graph that is involved. I don't need that computational graph. I just need the number. So just loss dot item, you get the number, and then you say that batch into batch size plus length of x, and that will give that now how much is the current size of them. Okay? This is just to print the statistics. This is the overall training one epoch. Now this you are doing it for each epoch. You are doing this. Okay, then you have test loop. Okay, now let's go to the test loop. Data loader, model, and loss function are the input. Now then you give model.eval. Now that means that you are saying that, okay, so now how many, you are saying that I'm working in the evaluation mode now. Okay, so and then what do? You go to the test loop. First you compute the size, now which is number of examples. Okay. Now then you have number of batches. How many batches are there? Now that also you take it into consideration. Size and number of batches. So now you should be evaluating, right? You should be evaluating how much is the loss and then how much is the correctly classified examples. For that, you need these two placeholders, which is now with torch.nograd. Now why is this torch.nograd is used? Now it just ensure that no gradients are computed in the block which is indented this. Now that means that in this whole block, there will be no gradients that are computed. Okay. Now you'll ask the question, now why do you need this? Okay, yeah, preferably we only need this. This is unnecessary, but this is added for best practices. Okay, fine. So now you iterate over the data loader, which is the test loader. Now you get x and y. Then you go ahead and pass it through the model. You get your predictions. Okay, and then you get your loss, and then add it to the test loss, which is there. You just need the item. You just need the numerical value of it. Good. So now you have added the loss. No, but now we are dealing with a classification problem. Now for us, the accuracy is much more important. What do you mean by this accuracy? Now that means that how many examples have I correctly classified? That I need to calculate. Now, how do I calculate it? See, I have obtained a probabilities. Okay. Now, what do I do? I have obtained a probability vector. Now let's take have P1, P2, and P3. This is I just have a 3-class classification. Now, if I calculate the highest, now which one is high? Which one is highest? Now to that class I'm putting, right? Now, which one is highest? That will give you a value. But I need the index, right? This is 0th index, first index, or second index. I need the I will be needing the highest. And what is the index of it? That is the next question. Okay, I get the index of it. Okay. Now let's say that your P2 is highest. Now and then you get the index as 1. Now then you say that this is correctly classified. Now when this 1, now this will be your y hat. This is same as y, which is your actual value. Then only say that it is correctly classified, right? Now I want to do this specific operation now. To do that, correct plus equals. That means that you are increasing it with the pred, which is your predictions dot argmax. Now you are taking the index of it, the first one, the top one. Now, is that same as the y? Now you are checking that is my prediction is same as the y. Okay. Now then it will be true or false, right? Now you will get a vector which is true or false. Okay. Now you have a batch. You will get a list of true or false. Now that true or false, you convert it into a torch float. Now that means that now true will be converted into 1 and false will be converted into 0. Okay. So now in a batch, now if there are 10 correctly classified things, I have 10 ones and the remainings are 0. Now if I sum all of them, now I will get 10, which is number of correctly classified example. I just take the item of it. That means I just take the number of it. Okay. Because of which my correct will be updated accordingly. Okay. So now and then to run this so that I can have the loss. I can show you that also. Now test loss. Now we are calculating per batch. So now you divide it by number of batches so that you can know that what's the test loss per batch. And then the correct, how many examples are correctly classified. That you divide by size, that you get the accuracy. And then you multiply that with 100, will give you the accuracy, and then you will get the test score of it. Yeah, you can see that. So how for each 100 thing you will things are incremented, and accuracy is 42.4, and then your loss is 2.16, and similarly. You can see that the accuracy is increasing and meanwhile the loss is decreasing. Okay. Now, in addition to this, normally one more thing that we do is we will have a list in which we append the losses and then we get a curve, which is this is epoch and loss values. Now, it is we need a trend like this. Okay. Okay. We need a trend something like this. That means that as the epoch goes, the loss which is there is reducing. Now after that, after some time, it will flatten. Okay, that means that there will be no much of a change. Okay. Now the next question that comes is how many times you should train it. Now, there is no standard answer for that. Now, we'll be looking at these questions when we start handling the tutorials on the generative models while coding them. Yeah. And how do you figure it out? All those things. How do you, in a simple way, we will figure it out. Don't worry on that as of now. Okay. As you can see that, we have given 10 epochs, so it will run for 10 epochs. The accuracy that we have achieved is 68.7. The accuracy should increase, but the loss should decrease. Okay, yeah, that should be evident from the discussion that we have. Now the training is done. Okay, this is the overall process now. Let me reiterate this. You prepare your data. If the data is available from PyTorch, directly take it. If it is not, you create a custom loader. You create the model. Yeah, what are the parameters that are there in the model? You should be aware of that. You take the hyperparameters. What is the loss that you are using? What is the optimizer that you are using? Train loop. When with the steps are first you predict, compute the loss, obtain the gradients, update the weights, make the gradients as zero. This is one additional. This is a programming step to be more specific. This is not a theoretical step. And similarly, you go ahead and perform the test and run it for whatever number of epochs now you want to do it. Now, this is how you optimize your. Now that means that you have obtained the optimal weights. Okay. Now you have obtained those theta, which is optimal. Okay, when which the loss is least in this optimization problem. Okay. So now the last step that is involved is how do you save these? How do you save this? Because every time whenever I want to reuse it, I don't want to rerun it again, retrain it. Okay, now you should be able to save it. Okay, so now I don't need this 1K, I just need these two statements. Now, whatever model it can be that you have saved, that you have now, torch.save, whatever model, this is the name of the model, this is a variable name, you can use whatever name you want. That in the current path, you save it as model.path, torch.save, the model, you save it as model.pth. Now that is the extension, pth is the extension of this, you store it like this. Now, this is how you save it. Now, if you want to load it, now how do you do it? Now you have the model. Okay. So, and then torch.load, you have created the instance of the model. Now, model.path, which is the name of this code, and then you only copy the weights only. Okay. You're not only copying the weights, now whatever is involved in that, you just copy everything. Okay. This is how you load the model. Now, these are some of the steps that are involved in looking at it. Now we have till now we have looked into the idea of how do you create a model. Preferably, we have created a MLP model. Now, at the fag end of the second tutorial, what we should be doing is now we shall be looking into how do you create a CNN model. Okay. Now that is the important thing. Now, whenever you have, I'm assuming that you are pretty much comfortable with CNNs. Okay. Now, let's look at the CNN models. Now, the first question that arises whenever you're considering the CNN model is how many layers? Okay. Now, once you have fixed this question, the second thing is okay. The second thing that arises is you should specify in each layer. You should specify in channel. That depends on the input that you have. Then you should specify the out channel. This out channel is same as number of filters that you have, and then you should be specifying the kernel size. Okay. we'll be using square kernels. So even if you say 5, now that means that you are using a 5 cross 5 kernel. And then what is a stride? You specify, and then you should specifying the padding. Okay. Now these 5 options now you should be specifying. Now, only the input channel here depends on what is the previous stage's input. Now that it depends. Other than that, you should be specifying these 4 parameters. And then once you have specified them, then now we are still dealing with an image classification problem. That means that you should be uh, deciding on the classification. Okay, deciding on the classification. Now, all the CNN models has some convolutional blocks. Let's say that I have convolution 1, I have this convolution 2, I have this convolution 3, which whatever parameters that you have is there. Now, after this, now you get a block. Now you get an image block, which you flatten it up, and then you need an MLP. Okay. Now this blocks of convolution layer, it is famously called as feature extractor. Okay, these are called as feature extractors. And then this MLP which is there, now this is what is called as the classification filter. Okay. Now we need to decide even on this before going ahead. And whenever an MLP comes into picture, yeah, the problems of how many layers. It's not like you have the input layer and then you have the output layer. How many hidden layers, how many nodes in those hidden layers. All those things also needs to be decided. And what is the activation function? Similarly, activation functions of all of these layers also needs to be decided. Okay. Yeah. And then you need to code it accordingly. Okay. So yeah, now the only thing that changes in that case is all your training loop loaders, everything remains same. Only the neural network that is there, now that will be changed to a convolutional block. Yeah. So now, whenever needed, now we shall be looking at this convolution layer. As of now, let's stop today's tutorials on these ideas. Just to give you a small recap of what are the things that we looked at today. Now we looked at tensors. What are tensors and how do you work with them? We looked at the data loaders. We looked at the transforms. How do you build the neural network? Specifically, we are looking at an MLP in that case. Now, in an MLP, what are the parameters that are involved and how do you work with them? We understood that. So, okay, and then the forward pass, and then the training loop, the test loop, and then how does you can have even a CNN model also as a model. Okay, so yeah, with this, let's conclude today's tutorials. From the next session, we shall be starting with the interesting stuff. We'll start coding GANs. Okay, thank you. Bye. See you in the next tutorials.